Okay, well, welcome back. Today we're going to be looking at microscopy and microanalysis techniques, and some of this is not in your book, so you really should print out the notes so you have a hard copy reference, and you can make notations on all the diagrams and stuff. So we want to talk about X-ray diffraction today, and we're going to spend quite a bit of time talking about the fundamental interactions of electrons and solids. Electrons are our friends in terms of analysis of materials. There's a lot of electron beam based instrumentation. We're not going to cover all of it. We're going to cover some of the most commonly used tools for the materials engineer, at least the mechanically oriented materials engineer. We're going to look at how the electron microscope works, the scanning electron microscope in particular, and also the transmission electron microscope. And then the goal is of all of this, my expectation for you is that you're going to be able to identify how to answer given materials questions. The answer is not always use the microscope, and you need to be able to identify the proper tool. So the first technique, your text has quite a bit of discussion of X-ray diffraction, and this is of tremendous interest to the materials scientist, not as big of an interest for the materials engineer, but in class we'll look at a couple of very useful applications of this. The key to X-ray diffraction is that crystal structures interact with incident electromagnetic radiation of all kinds. For light, we get total reflectance. Gamma radiation is totally absorbed usually. X-rays are diffracted, and that is, as the X-ray beam impinges on the surface, the photons, the beam photons, are bent, and they leave the surface at an angle. And so this is called diffraction. Now, you've seen this if you've been fishing and you notice that your fishing line comes off of your pole and at a certain angle, and it appears to be bent at the water, and that's caused by the light being diffracted as it passes the interface of the water, and so it doesn't come to your eye aligned with its original source. So this diffraction occurs at any interface where there's significant interaction, and it can happen in visible light as well as X-rays. But for metals and crystalline materials, the crystals interact by diffracting X-rays in particular. Now, how is this used? Well, basically what we're going to do is shoot X-rays at a sample, and then we're going to measure the intensity of the X-ray beam that's striking a detector. And in the old days, if you're Francis Crick discovering the structure of DNA, you literally have a device that looks like a toy train track on a stand that's about the size of a room, and your detector runs on wheels around this track. And they suffered from limitations of electronics, and to get very accurate angular measurements, they needed a very large path so that they could get very fine angular position measurements. And modern instruments don't do this, but this is much easier to visualize. So we're going to shoot the beam. This detector is going to move along the track and just measuring how intense the beam is that's hitting it, and we're going to plot intensity of the beam versus angle, the diffraction angle, as we move along the track. And what you see is there are particular angles that give us large peaks, 45, 65, and about 82 or 83 in this case. Now, it turns out this is a fingerprint. This is very useful if we want to know certain bits of structural information. And if you remember our in-class work, these are Miller indices. They refer to planes within the crystal. So what can we get from X-ray diffraction or X-ray scattering? It's usually called XRD, or X-ray diffraction experiments. We can identify the crystal structure. That is, particular crystal structures, in this case, let's say FCC, will have diffraction on three planes, the 111, 200, and the 220 plane. And so there will be three peaks. If we go back to the spectrum, you see there's three peaks, 110, 200, 211. You calculate from the lattice parameters, that is the size of the crystal unit cell and the properties of the plane, you calculate what the diffraction planes are likely to be. And so that spectrum obviously came from an FCC crystal. It had three peaks, and that they are associated with these three planes. And then BCC has a different set, and so on. So here's the key. We can get lattice constants. We can identify the type of crystal, FCC, BCC, HCP, simple cubic, whatever. We can determine lattice constants. That is, you actually can measure the size of the crystal from the peak locations. But it doesn't tell us composition. And one of the things we're most often interested in materials problems for an engineer is composition. And X-ray diffraction, XRD, won't give us that. Now, modern XRDs are not very exciting. They look like a telephone booth. And because what we do now is rather than have the detector on a big track and a goniometer, the sample sits in here and is rotated and the beam source is kept constant, and then you have a detector off to the side. And as you rotate the sample, very precisely using modern instrumentation, you can then measure the angle of diffraction. So kind of boring looking anyway, but that's what a modern XRD looks like. So XRD, X-ray diffraction, cannot tell you which of these. Composition, that is, who is present, what elements are we playing with. It will tell you crystal structure, and you can use it to measure lattice constants. Okay, so that's XRD. That's probably all most engineers need to know about that. The electron microscope, though, is a whole other animal. And at the heart of the electron microscope is the electron gun and the electro-optical system. And so this is used for a lot of different instruments, and we can pull a lot of different kind of information from a sample. And the operating principles are identical to the operating principles of the cathode ray tube at the back of an old television set. So before flat screen TVs, you had those big deep TVs with the thing poking out of the back. That is essentially an electron gun. And so it begins with a cathode, and this is usually a tungsten wire filament, just like in a light bulb. And this cathode is superheated by running a very high current through it. And that superheated cathode begins to spit loose electrons. Now we apply then a very high voltage. We're talking keV, thousands of volts. And most SEMs operate between 5 keV and 25 keV. So very high energies. We're going to accelerate those electrons through there's usually just a cover around the electrode, but through an aperture. As the beam gets going, it's going to go through this aperture, and we're going to then get a nice stream of electrons we can play with. You then have lenses that condense that beam. The goal is what's coming off of here is about the size of the aperture, which is fairly large, and we need a very, very small beam. And so we have to squish those electrons down into a tightly focused stream. And you can think about how do you push on electrons? Well, they're charged. And so you can either use charge to push on them, or in this case, they're a moving charge, which means they have a magnetic field. And it's easier to push on a magnetic field with a magnetic field than to push on a charge with a charge. So these are electromagnets. They focus the beam down, make it very, very small. You then have one last set of focusing magnets that are your objective lens. And the actual optics here follow a lot of the same rules of optical microscope design. These are really condenser lenses. You have condenser lenses in binoculars and in telescopes and microscopes. And a lot of the geometry of this optics works out the same. However, this differs dramatically in that we have a tiny stream that we're focusing, and we're going to scan that stream of electrons over the specimen. We're not going to shoot at a single point. We're going to aim it at a point, and then we're going to move it around on the surface. And so we have scan coils. These are more electromagnets that cause the beam to deflect. Final aperture, and then you'll have detectors, and we'll talk about detectors a little bit. So the way an electron beam instrument usually works is we're going to scan the beam over the surface in a raster pattern, and we're then going to look at what comes out of that scanned surface. So though you see a picture, it isn't remotely similar to a light type microscope, because in a light microscope, you're bouncing the light off the surface and seeing the light. Here, we usually don't look at the electrons we're shooting at the surface. Most of the time, we're going to shoot them at the surface and knock stuff loose and look at what's knocked loose. So we're going to be scanning it over the area of interest and generating information over this area. The way your television works is this beam scans along the screen, the old-style TVs anyway, scans the surface of the screen, the glass on the front, and that glass is coated with a material that absorbs energy from the electrons and then decays back down to a low energy state and fluoresces, releases that energy as light almost identical in operation to a fluorescent light bulb, where we excite the molecules and they emit photons of visible light. And so there's some interesting things we'll talk about. When you shoot an electron beam at a surface, some of the products are a little bit scary. And when you're watching television, old-style TV, you're actually looking at some of that stuff. So here's a modern SEM, not real exciting anymore. Computers have made them very boring. There used to be masses of lights and knobs and all kinds of mad sciencey stuff. And now you just push a button and the SEM works. So we have one in the lab that is functional, usually, and we'll hopefully you'll have an opportunity, some of you, to use it in your projects this semester. All right, so as we think about that beam we're aiming at the surface, we need to recognize that electrons are little bitty things, and a surface of a solid is still mostly empty space. There isn't much there. So when an electron hits the surface, some electrons may bounce back, but most electrons penetrate into the surface. And as they penetrate, they may interfere or bump into other electrons, and so they're going to tend to scatter, and they spread out under the surface of the material. And that spreading out gives us a volume of material where electrons are interacting with the material. We call that the interaction volume. It kind of looks like a light bulb. It's three-dimensional, it's narrow at the top, and it spreads out into a bulb, like an old-fashioned light bulb. And that is an issue because we have to recognize that the higher power of our beam, the deeper the electrons are going to go, and whatever signals we are looking at are coming from where the electrons have gone. And that may not be the surface. We may be seeing a lot of signal that's actually generated from deep in the material. So you have to understand this basic relationship so that if you're trying to look only at surface effects, you turn the energy down. You want to minimize the energy of your electrons so they don't send you stuff from down here deep in the material. All right, having said that, what do you think is going to happen if we have a low atomic number? What's going to happen to the depth of the interaction volume? And of course, it should be much deeper. Low atomic number elements are going to be small nuclei, and that means you're going to have less likelihood of the electrons being deflected, and they're going to tend to penetrate farther into the material. So interaction volumes are deeper. All right. So if we shoot these electrons at a surface, the surface isn't completely empty space, obviously. And so the first kind of product that may come from the surface is a product of elastic scattering. And in elastic collisions in physics, we call that Myths and Legends 101, there are no perfectly elastic collisions except at the level of electrons, where it is possible for an electron to go in with 20 keV of energy and come back with 20 keV of energy. No energy transferred. We say they are backscattered particles. So they may be very hot. And what we're going to do is we'll shoot the beam at a point on the surface. We'll have a detector that when it is hit by electrons, it fluoresces. And then you simply have a photodetector at the end of this that turns that fluorescence into a voltage. And so if a lot of electrons hit the surface, so a bunch bounce over, we get a bright fluorescence and we get a high voltage, and that'll be sent to your computer as a high voltage, and that'll show up as a bright spot on your screen. If only a few electrons hit the detector, it doesn't fluoresce very brightly, you get a small voltage, you get a dark spot on the screen. And we're going to build a picture by scanning across, and at every point getting an intensity of the backscattered electrons, and from that we get an image. So basic principle here, backscattered electrons, they're going to bounce off the surface, and they're going to go where they want to go. They have a lot of energy. The detector has to be in the way, or they don't hit it. And so you're going to try to put this detector here at as high of an angle as you can get away with to try to maximize the signal that you get. All right, so that's all we get for elastic events. So everything else that happens involves the electrons giving away energy. And there's a host of these things that can happen. The two simplest are phonons and plasmons. And that is the electrons can give away energy and can cause the nuclei to get hot, to vibrate a little more, give them kinetic energy, and that's called a phonon. They can also give up energy to the electrons in the solid or in the target, and that's called a plasmon. So those are really cool terms. Sounds like something that Mr. Scott would use, or whoever your favorite Star Trek engineer is. But these are actual scientific terms, phonons and plasmons, measures of kinetic energy of the particles. Now, We can also get energy given away as X-rays, and this is called Bremsstrahlung X-ray, which is the coolest name you have all semester. But what happens here is as a charged electron moves through the coulombic or the charge field of the nuclei, they're positively charged, they're going to grab at it, they're going to slow it down. Well, you know, electrons don't have brakes. Your car uses brakes to convert kinetic energy into heat. If an electron is going to slow down, it's going to lose kinetic energy. It has to give away the energy as something, and it gives it away as a photon, not a torpedo, but a photon, which is a particle, essentially, of light, or in this case, an X-ray photon. And so when electrons hit a solid and slow down, they emit X-rays. Now, the problem with Bremsstrahlung X-rays, besides the fact that they're hazardous because they're X-rays, is that they're emitted at every possible wavelength, every possible energy level. It's just noise. So you get this X-ray noise anytime you shoot an electron beam at something. If you think back to televisions, back in the early 60s when color television was young, and color television has 3 electron guns going, and they were very powerful because the phosphors on those TVs were not very good. You had to hit them with really powerful electrons to make them fluoresce. You had measurable X-ray doses at the screen. And so if you stood real close to your television, it was like getting an X-ray. So children were told they had to sit back from the television or they'd get brain cancer. Anyway, whether that was really a risk or not, I don't know, but we were scared. So, okay, so that's Bremsstrahlung. That's not useful. So the heat is potentially useful. We do use electron beams for welding. And in processes, you can ask your professor about electron beam welding. That's pretty cool. We have a lot of useful inelastic particles or inelastic scattering events, though. And the first of these is called a characteristic X-ray. So we're going to get another kind of X-ray, but this one is actually helpful. And what happens here is a photon of energy is transferred to an inner shell electron. So here's a nucleus, there's my first shell, there's the second shell. Third shell has empty spaces in this case, empty energy levels. So this photon is absorbed by an outer electron, which is excited to the next available energy level. Now, there's an empty space that's been created in this inner shell, so that photon is not going to stay at this high energy. All systems seek the lowest possible free energy. So if this electron doesn't decay back, somebody else out here will refill this energy level, and it has to get rid of the energy that it has at the higher level. It's going to emit an X-ray photon. The difference is, if you remember from our discussion of structure of atoms, these energy levels are quantized. That is, they're steps. Only certain energy levels exist, which means these photons will have only particular energy levels. They're not continuous like the Bremsstrahlung X-rays are. These are going to only occur at certain levels. So as the electron decays down, fills the inner energy level, it emits a photon that has this energy level. So if we look at the hydrogen atom, hydrogen only has the one shell, has one electron in it, so there's an empty space here. But if we were to excite an electron out and then it decayed, these are the possible energy steps from all of the levels out to, what is that, 8, all the way down to the minimum. But you can measure decays to n equals 2 shell, n equals 3. These are all measurable. These are small energies. So the ones that are easily picked up are these guys because they're very large. The photons have a tremendous amount of energy. But theoretically, you could look at all of these to identify the material that your elements, or that your X-rays are coming from. And the key here is if we measure the X-rays coming out of a material, and we're going to plot literally the number of photons hitting a detector versus the energy of those photons. So this is energy in keV. This is the number of photons striking the detector, and we find, there's noise, there's your Bremsstrahlung. You're going to get photons at every energy level. But we have peaks where we're getting a lot of photons. Those are associated with the particular decays, and the combination of peaks is unique to a given element. So this is silver, has these peaks, and that's actually a peak, but not used usually for identification. Uranium's pretty noisy, it's a heavier element, and these are probably the peaks used, but sometimes when you're separating it from a similar element, they have similar inner energy levels, you'll end up looking at this one as well. So heavier elements have more peaks because they have more available energy levels for decay, and so you'll see a lot more peaks going on. All right, so these X-rays tell us who is home, what elements are present, and that's often the big question. What impurities slipped through our process? Is the alloy the right composition? And so on. And so this is a very useful tool. The other inelastic scattering that we make use of is called a secondary electron. And basically your beam electron comes through, and it's kind of like a pool table situation, and you're going to kick out an outer electron here. Now, generally, the energy of these electrons is less than 50 electron volts. Not very high energy. So they don't come from very deep in the material. They don't have enough energy to escape from way into the surface. They can only escape from the top, a shallower top layer. And because they're low energy, we can do some cool stuff with them. And we'll look at that when we get to imaging. And then the last inelastic product that's of interest is kind of the ultimate ping pong or pool table trick here. We're going to start out like a characteristic X-ray. So the beam electron ejects an inner electron. Then an outer electron decays down, and it emits an X-ray photon, but that X-ray photon doesn't make it out of the atom. Instead, it's absorbed by another valence electron, which is kicked out. Now, it's too much energy to remain. It doesn't just move up a layer, it leaves. And it leaves with the energy of that X-ray photon. Not much energy, in other words. And so these are called Auger electrons. Although it's spelled Auger, it's Auger. And they don't have a lot of energy, but again, they have the wavelength or the energy level of the photon they absorb, so they're just like a characteristic X-ray. They will tell you what element they're from, but because they don't have much energy, they can only escape from the surface of the material, the top few atoms. If they're emitted in the interior of the material, they're going to run into something on the way to the surface. They're never going to get out. Also, because they have such low energy, they're very difficult to measure. And you have to have ultra vacuum, a better vacuum than space, and you have to have very sensitive detectors to find them. So Auger spectroscopies are relatively expensive, but if you want to know surface chemistry, then it's the way to go. It'll give you just the surface behavior. And of course, this is materials engineering. In materials engineering, we're worried about failure. And the three biggest causes of failure are corrosion, wear, and fatigue. Corrosion is entirely a surface phenomenon. Wear is a surface phenomenon. And fatigue mostly begins at surfaces. So we care a great deal about surface chemistry, the atoms that are actually interacting with the outside environment. So it's a very powerful tool for understanding surface chemistry and surface behavior. Okay, so this is all the different interactions. How do we take pictures? And this is what we will do, hopefully we'll be able to do in the lab. Backscatter electrons, we're going to make a picture, and it's going to be very different than the picture we can make from secondary electrons. And the key here is backscatter electrons are fast, so it's like shining a flashlight at something and seeing what bounces back. Secondary electrons are not so fast, so we're going to be able to cheat. And we're going to be able to see around corners, actually, with secondary electrons. So when we're taking a picture, we have to basically count the number of electrons coming from every point on the surface as the beam scans. For backscatter, we're going to see the electrons that bounce to the detector. Now you notice this detector has a polarization. They put a negative 50 volt potential on it. And the reason you do that is secondary electrons, if you remember back, all the way back, sorry. Oh, wait a minute, where was it? I skipped, there it is. Okay. Secondary electrons have an energy level less than 50 eV. So the idea here is if we put a negative 50 volt potential here, secondary electrons are going to be repelled by this detector. They're not going to hit it. So they're generated, but they don't hit this detector. The only things that hit this detector have to have higher than 50 volt energy. They can fight through that. Well, the backscatter electrons have thousands of volts of energy because they have the same energy they came in with. So they punch through that and they hit the detector. But if the surface is sloped away from the detector, not much is going to bounce towards it. So we're going to get shadowing. And it's like shining a flashlight at the surface and standing off to the side. And if the stuff's reflected away, you don't see anything. Secondary electrons, on the other hand, we're going to put a voltage on the detector, 200 volts. It's going to act like a vacuum cleaner. And so as they come off the surface, they're going to get pulled over here, just sucked over, and they hit the detector. We're going to catch the vast majority of the electrons that are being released from the surface. When the surface is sloped away, some of them will end up escaping. They're going too fast and too much the wrong direction. But even here, we're going to get some of them captured. And so what you'll find is that secondary imaging usually gives you prettier pictures because you don't get strong shadowing effects from the images. So how do they look differently? What's the difference? Well, these are not the same area exactly, but they are, one of them is a backscatter and one is a secondary image of the same kind of surface. And you notice a few things. You can usually tell where the detector is based on where the bright spots are. So in this left image, the detector's up to the upper left. Here, these bright surfaces suggest the detector's to the upper right. Other than that, you see a lot of fine gray. There's a lot of nice detail. I don't see a lot of stark blacks here anywhere. Okay, you see this tends to be very contrasty. It's bright or it's dark. There's not a whole lot of gray in between. This is a backscatter image, the one on the left, and this is a secondary image. And generally, these are more pleasing aesthetically, and often there's more information because extreme contrasts tend to hide fine detail. And so we like secondary imaging where you're looking for fine detail. Backscatter electrons have another feature, though, another thing that's nice about them. This is a backscatter image of a lead-tin alloy. And because the backscatter electrons are bouncing off, essentially, the atoms, lead is going to bounce more electrons back than the tin will. And so in this alloy, we don't have uniform composition. The bright areas are bouncing more electrons back than the dark areas, and due to compositional differences. So we don't know what they are from the image, but we can tell where the heavy elements are and where the light elements are. And so if we know composition, then we know who's where. So that's a nice feature of backscatter imaging. It's compositional sensitivity to an extent. Okay, so which of these only gives you surface structure information? Pause the recording. Okay, and the answer would be secondary electrons, right? Only give you surface structure. Backscatters also give you composition. These are composition characteristic X-rays, Auger's composition, and X-ray diffraction is crystal structure, not surface structure. All right. Now, interpreting electron images requires that you train your brain a little bit. Your brain's going to make sense of the image it sees, but an electron image is not the same as a light image. And a big difference arises from this. Secondary electrons will escape from a particular depth. Anything that is emitted within this distance, the blue arrow, can escape. So when the beam hits, the interaction volume, the light bulb, is where secondary electrons are being emitted, but I only get the ones that are generated near the surface. Now, if this is a slope, when the beam hits, we're going to get electrons that are generated not only up here in the base of the bulb, but also from the shoulder. So a slope will actually give you more electrons than a flat surface will. A light microscope, on the other hand, a slope is going to scatter the light. You're going to get less electrons. So a way to think about this, here we're looking at an electron microscope image. The top flat part of these particles is darker than the edges. More electrons are escaping from the edges. And notice the flat surface here is not very bright. With a light microscope, or this is not a light microscope, but with light, what you see is the center of the rock is bright and the edges that are falling away are dark. But this isn't a true negative because a hole here is still black. And a hole here will still be black as well because no light's escaping, no electrons are escaping. So interpretation, your brain instantly does it. It's amazing. Your brain is an amazing tool. It makes sense of this picture. But when you're looking and trying to identify whether something's a hole or a hill, sometimes you need to think through where is it bright, where is it dark. So to test your skills here, we'll highlight this as well. This also shows up when we talk about fine surface roughness. So with a light microscope, fine surface roughness causes scattering. We've already seen this picture last class. And so you get dark, light, dark, based on the surface roughness. Well, with an electron microscope, your secondary electron emission is going to be greater if there's surface roughness. So a slightly rough surface will be brighter than a smooth surface will be. So you have to watch out. Edges will produce signal, and so you're going to get brightness. So can you, now considering those ideas, and remember in this summary, flat surfaces optically, flat surfaces are bright. In the SEM, they're dark. Rough surfaces are slopes. Optically, they're usually going to be darker. In an SEM, they're going to be bright. But remember, holes are still black because nothing gets out of a hole. So it's not a negative. So can you tell me, or tell yourself, is this a hole or a hill? Pause the video, sort it out, decide what you think it is, and then restart. All right, you should have said this is a hole. Now, if you notice, at the edge, this is very bright. Right? And in a light microscope, edges don't show up. They're just, it would be surface coming to surface, the top of the hill, or surface coming to the bottom of the hole, and there's no delineation. We get this bright light here. Now the question is this the edge of a hole or the edge of a hill? And the hint is if this was a hill, the top of the hill should look like the plane around it. Should be about the same intensity. But this is down in a hole, so fewer electrons are able to get out, so we're getting a darker return from a flat surface. Okay? So this is actually a bubble in paint on a button, one of those little buttons on your car radio. So we're looking in a broken bubble. And that's the layer of paint below the surface, or maybe the plastic underneath. All right. The last type of electron beam instrument that's really important and is the transmission electron microscope. And the idea here is we have a similar electron coil, and there's our filament that generates electrons. It goes through condensers and through an objective lens. And we put a sample right here, and the sample is very thin. It's been microtomed, it's called, often cut in cryogenic conditions, particularly if it's a polymer or an organic material. It needs to be hard, so you can cut it really thin. And so the specimen is here, and you shoot the beam through it. And usually you scan the beam, and then you go through a bunch of optics, and you're going to then see bright where the beam comes through uninterrupted and dark where the beam is interfered with. And usually we will have to treat the materials with a dopant, particularly organic materials, polymers, and biological samples. So you put some heavy elements in certain areas so that they absorb electrons better. This was actually the first kind of electron microscope very early in the 20th century. The SEM didn't actually come into existence until the 50s, even though the physics is not any different than this one, and it could have been done much earlier. And you get images like this. Now the key to understand about the TEM, the transmission electron microscope, is your resolution is much, much finer. You can see really small things. These are dislocations. These are stacks of dislocations, stacking faults. These are precipitated oxides in aluminum, stir-welded aluminum. They're aluminum, copper, magnesium precipitates in 2024 aluminum. And so these are tiny crystals, and you look, this is 200 nanometers for this line scale. So some of these particles are on the order of 10 to 20 nanometers. So we're seeing nanoscale structures in the TEM, and have been able to since at least the 50s, when TEMs became very mature technologies. Unfortunately, you can only see things in section. And so this didn't really get nanotechnology launched because you couldn't look at surfaces. And as we've already discussed with defects and particles and energies of surfaces, surfaces are where the action is. So the key revolution for nanotechnology has been the ability to look at things on surfaces at the nanoscale, not in section, because we've been doing that for actually quite a long time. All right, and that completes this section, and next class we will begin discussion of diffusion.